And welcome to another level 3 5-minute video. In this session we'll talk about coating pigments. The main pigments we'll talk about will be clay, as a typical clay particle. As you can see, hexagonal shaped, interesting type of particle, positively charged around its edges, negatively charged on the top. Clay particles don't exist on their own, they normally exist in little stacks. Chemically, these are aluminosilicates. So they exist in stacks, and this stack can expand or contract depending on the moisture that's available and the pH of the environment. Clay particles are very flat, as you can see, so these are typically used for making glossy coatings. Chemically, they're relatively inert, and the flatness means they're really good for providing glossy coatings. There's another type of clay called calcined clay, and this is a bit what calcined clay looks like. You essentially take an ordinary set of clay stacks and you subject them to very high heat in a rotary kiln, and they all fall apart and they fuse together to form these type of shapes. So, formed by the high temperature treatment of regular clay. Because of these, imagine these particles turning around when you're mixing them. You see how easy it is for these particles to interlock. Well, that happens. So this we call shear thickening. So the faster you stir it, the thicker it will go. Stir it fast enough, it'll settle like concrete. And then leave it alone, it'll go back to being liquid again. So this is when we talk about rheology of fluids, and this is termed dilatancy, when things shear thicken. And these type of particles actually produce quite bulky coatings. So if you need a bulky coating for some reason, then calcined clays are the way to go, but you've got to be careful how you physically handle them. Calcium carbonate is another very commonly used pigment, and there's two types of calcium carbonate we'll talk about here. There's natural calcium carbonates that you dig up out of the ground, and there's man-made calcium carbonates, or PCC as we call them. So these are typical micrographs of calcium carbonate-like material. As you see, they are typically round-ish particles, but with not have a smooth surface, almost like little micron-sized cauliflowers, or 10 micron-sized cauliflowers. So the good thing about chalk is it's quite high brightness. You can get high solids contents. When you're buying slurries of calcium carbonate, you can get probably 70, 71, maybe 72% solids contents, whereas with clay you're probably limited to about 65, 66% solids. They do speed up the rate of ink drying, and they have a low binder demand. Remember, binder only reacts with the surface of a particle, and for any one volume, if you think of all the different shapes that there are, be them sort of pyramids or cubes or spheres, then the sphere has the smallest surface area for the same volume. So this is one of the things that contributes to the lower binder demand of calcium carbonates. There are some negative things as well. So it's a very soft pigment, so coatings with calcium carbonate in scuff very easily. They reduce the gloss because of the way that the ink interacts, then you don't get very glossy ink surfaces. And it's also fairly poor hiding power, so you need quite a high concentration to hide what's below. PCC I mentioned to you before, that's precipitated calcium carbonate. So this is a man-made calcium carbonate rather than digging up all those old bones. So PCC, as you see, a completely different structure. PCC is man-made from mill flue gases. So you've got the tall chimney. You've got to have a big enough mill to make this economically viable, but you've got the big tall chimney from the mill that all your flue gases go up, high levels of carbon dioxide there. So rather than just venting it to atmosphere, you bubble it through lime water. You get a reaction then between the carbon dioxide in the flue gases and the lime water, and you produce calcium carbonate. So it's a great way for carbon capture and storage. And the properties are exactly the same, really. High brightness, high solids, fast ink drying, low binder demand, scuffs easily, reduces ink loss, and it has sort of poor hiding power. TiO2, this is probably 10 times or more expensive than any of the other pigments, so it's incredibly expensive, so we tend to use it sparingly. At the point of making this video, calcium carbonates and clays are probably around £150 a tonne. TiO2 is probably around £6,500 a tonne, just to give you an idea of relative costs. TiO2 comes in two crystal structures. One form is anatase, another form is rutile. So because there are two different ways of putting the titanium and oxygen molecules around each other, atoms around each other, to give these two crystal structures, they have different volumes, therefore they have different densities and different SGs, different specific gravities, and therefore different refractive indexes. So it's the highest refractive index of any pigment. Most pigments are around 1.4, 1.5, 1.6. TiO2 very, very roughly 2.6. So it's head and shoulders above everything else. Very expensive, as I mentioned before. The interesting thing about TiO2 is it interacts with UV light. It absorbs UV light and then reflects it, re-emits it, and gives out a little bit of energy. That might sound a bit familiar to you if you think about optical brightening agents. So one thing you should never do, ever, is to mix optical brightening agents and TiO2 in the same formulation, because they both want to react with UV light, they are both expensive, and typically the TiO2 wins. So you'd just be wasting your money with OBAs. In fact, TiO2 will act as an OBA quencher, and it's actually used as such in some products. And satin white, this is a calcium aluminium silicate, very high pH, around about pH 11 or higher, and it's typically used in conjunction with casein, which is a binder that's derived from milk products, and it's used in the cast coating process. Cast coating process is used less and less these days. It's a very, very slow process, therefore the overhead cost is tremendously high, and so the products are very, very high added value. So it produces the highest quality, the highest gloss of all coated grades. Sadly, people have learned to mimic the gloss now by using cheaper coatings and then just printing over it with an overprint varnish. But at one point, this was the best of all coatings. So a summary of coating pigments. Coating pigments want to be small, typically 1 micron or less. They need to be inert, so chemically unreactive. They want to have a high refractive index so they've got good hiding power. And they want to be bright, and they usually are brighter than fibres. The only difference between a coating pigment and a filler, chemically the same, the only difference is particle size. Pigments have been ground and they're a lot smaller than what we put in the base sheet, which we then call a filler. Okay, well, thank you for listening to this video, and please feel free to follow us on any of this social media.